Hello everyone, this is the Unnamed here with the chemistry tutorial video. Now this is going to be the first in a series aimed at GCSE level chemistry, although I've slipped in one or two bits of information here and there which might be of a higher level, which might let you get the better of your classmates, or you might just find it interesting, I don't know. Either way, I hope this gives you a hand and with whatever you're struggling with, and yeah, I hope it's enjoyable. So the first one here, we're going to start from the very bottom, or the very basics as it were. So this is going to be on solids, liquids and gases, changing state and diffusion. So if you, well, let's go back to the beginning. You got three changes of state. You've got solid, liquid and gas. Already the pen is running out. That's a good start. Anyway, so you've got already three states of matter. So it's, you know, all the basics. The solids, you've got your kind of crystalline form, so everything's lined up like soldiers, as it were. Liquid, it's all closely packed. Molecules are exerting forces on each other, but they are still kind of not quite ordered. And the gas, where everything's going crazy and nothing's near each other, and they're sort of all over the place. So that's your kind of basic diagram of the first three, if you like. Now, if you think about it, if you think about a block of ice, bosh, there it is, nice and cold. Changing to water, what happens? The temperature changes, obviously. So, you think to yourself, right, here's a temperature graph. If you were sat there with a beaker of ice and a thermometer in it, and you've got temperature going up this scale here, so we'll put here temperature, and then along here you've got time, obviously. You would think to yourself, right, okay, so the ice is heating up, there it goes. Hot, 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 hot. Now it's water. Now it's water. After a while, now it's gas. Now it's gas. Now it's gone. All of it's gone. But you've got straight line. That is wrong. That is completely wrong, and it's counterintuitive because that's what you'd expect. Now this is more what you'd expect here. So over the wrong graph, here is the right graph. So what you've got here is basically, as you go up here, you've got your ice at minus 20 degrees, or very, very cold. As it heats up, it does heat up linear, so you won't experience any sort of change there. But as it reaches 0 degrees, okay, so that's obviously freezing point of water, so that's when it would change to ice, you've got a period of constant temperature, okay? And you'll see again, up at 100 degrees, where the water boils and turns into water vapor or steam, you have a period of constant temperature. Now, that you would not expect, because you would think, why would it just randomly stop heating? Now there is a reason for that. So if you'd imagine here what you've got, we'll look at these two diagrams first just here. I've drawn these on myself, obviously, so if they're a bit shoddy, let me know in the comments section if there is one. So first of all, what you've got here is your solids, or your solid. Okay, so imagine this is at minus 20. It's not moving very much. It's very, very cold. The molecules don't have any kind of energy, so they are all very stationary. As you begin to warm it up, temperature is basically relative to kinetic energy. Temperature is a measure of the average movement or kinetic energy of the molecules. So as you heat it up, you can see by these very, very obvious red little marks here that they're starting to vibrate and move around. This is an increase in kinetic energy, as I've said. So as you go up here, up this part of the graph, it's quite small and quite hard to see actually, I'm sorry about that. As you go up this first part of the graph, here, you've got your temperature increasing, your kinetic energy is increasing. Suddenly it's stopped. It's all stopped. Why has it stopped? Why is it stopped? Well, what we've got here is, you can see down here, your particles from before that you've made start to move here with all this kinetic energy, suddenly have all broken apart, or a solid into a liquid. They all started to kind of drift away from each other. So basically what we've got, as I've written at the side here, when you're heating up a solid but it hasn't changed into a liquid yet, you've got increasing temperature and increasing kinetic energy. Down below, you've got a stable temperature. This is during the flat period, of course. You've got a stable temperature, stable kinetic energy, therefore, but the bonds between molecules are broken. This is the key part. So, energy is always constantly flowing into your solid. That's why it increases its temperature. When it starts to melt, the average kinetic energy does not increase any further. And this is because energy is being pumped in to break the bonds between your molecules. So if you can imagine, go back to the sheet here. We've got, obviously, ice is made up of water, so that's H2O. Oh my goodness me, this is really running out. So this is your water molecule. So it's linked to multiple other water molecules here. And this would go on in a crystalline structure forever and ever and ever because it's a big block of ice. And in here you've got a bond called a hydrogen bond. That's all come up later on. So in here you've got your water molecules all packed nice and closely together. As you heat them up, they start to move around. They're all next to each other, but they're still moving around a bit. As you reach 0 degrees C, what happens is that the energy being pumped in by your Bunsen burner maybe goes into breaking this bond, or other bonds, such as you might come across a thing called van der Waals forces, which is a force that exists between most molecules in the known world. But hydrogen bonds, keep that in mind for the first. Basically, energy is going in to break the bonds, and that's why you don't see a rise in temperature. So, that is called, well, no, okay, we'll do that. In here, that's a specific amount of energy, and that will be specific between different molecules. It will be specific between different liquids, between different solids. Every single, for instance, water will have a different one to ethanol. So what that means is that everything has a specific energy value. Now that can be worked out, and this is where you might cross over with some physics. This is a value called the latent heat. And latent comes from Latin, I think, which means hidden. So it's your hidden energy, it's the energy required to break or overcome a hidden barrier, and that is the forces holding the molecules together. So the formula that you'll find for this is E is equal to M L. That's an L. It's a funny L. So here you've got your energy is equal to your mass multiplied by your specific latent heat. So your energy, you're measuring it in joules, big J. Your mass is in kilograms, little k, little g, and then specific latent heat is obviously going to be measured in joules per kilogram. So that's a little bit of crossover which you might find interesting. But aside from that, that is basically the mystery solved. So if we go back to our graph, what we can say here is as your temperature is going up and up, it stopped here. Okay, energy is going in to the bonds between water linked in ice, turn it into water. Suddenly it's all water. Now we're increasing the average kinetic energy of the water. It's getting faster and faster. Maybe one or two are starting to jump off the surface and be lost to the air. We'll keep going, we'll reach 100 degrees C. What happens now? All of a sudden, the bonds between the water molecules are being broken, and they're turning into water vapor. Basically, that is the final stage. The molecules, there's so much energy, they all have so much energy that they can't hold on to each other any longer, and they all fly off, and they become steam. And that's why water boils away. So that's that done with. The next part I said I was going to talk about would be diffusion. Now, I'm assuming everyone knows the basic principles of diffusion. You've got, if you spray some air freshener in the corner of a room, eventually in the other corner of the room, the opposite corner, you'll be able to smell it. Now, that's because particles move in a random motion, and that is just because they will bounce off other particles in the atmosphere. They will bounce off, pretty much anything. And that's certain for everything in the air around you. Now, you can change the rate of diffusion by several things. So if we just, that's gone through. So if we say here diffusion, I will get a new pen, I promise. Now, there's certain things that are obvious. Temperature, as we've just discussed, this increases the kinetic energy. So if we increase the kinetic energy, that will be an increased temperature, would lead to an increase in kinetic energy, and that will ultimately lead us to particles moving faster. So what happens if particles are moving faster? Well, it's obvious. If you've got your air freshener, you spray it in the corner of a room, and then all of a sudden you put a big fire in the middle, all of the molecules are going to move faster, diffusion is going to happen faster. So if we write at the end, we'll say faster. Okay. Ultimately, if you cool the temperature down, the opposite will happen, and if you put a big ice block in the middle of the room, everything will slow down a little bit, not by a huge amount. But another thing, diffusion is much faster in gases than it is liquids, and well, I mean, you can't dissolve anything in a solid particularly well. There are exceptions, but if you sprayed an air freshener in the ocean, it's going to take a long time, or a longer time, for it to spread out. And maybe that's a bad example, because obviously you've got waves which will move it around, but if you sprayed it into a glass of water, it will take much longer to travel in water than it does in air, and that's because the density of water is that much higher. So, looking at that idea of density, you may or may not have seen this diagram before. So what you've got here is basically a big long glass tube with two bits of wool at the end, which I've coloured to show that they're different. Now, in your left bit of wool, you've got ammonia here. So this is obviously nitrogen, 3 hydrogens, and then on this end you've got hydrochloric acid, or this is wool soaked in the solutions of ammonia and hydrochloric acid. Now, if you combine ammonia and hydrochloric acid, you get a compound called ammonium chloride, which is NH4Cl. That is obviously just an addition of NH3 and HCl, so you've got 4 H's and the Cl added. This is a white solid, so basically what happens is that your two gases will move towards each other by Brownian motion, by diffusion, and they will meet somewhere in the middle. And you can see here, by this beautiful drawing, and they're formed sort of more towards the hydrochloric acid than the ammonia. Now, there's a reason for that. If you look at the masses of these particles, you will see, let me get some paper, you will see that the mass of hydrochloric acid, there we go, is 1 for the hydrogen, plus 35.5 for your chlorine, which gives you a total 36.5. Okay, now that's fairly heavy for a small molecule. If you look for ammonia, you'll have nitrogen, 3 hydrogens, and that is 3 times your 1, that's for your hydrogen, plus your 14 for your nitrogen, which is 17. So you can see immediately that this is much heavier. Okay, now because this is, oh, that's beautiful spelling. Because it's that much heavier, basically what happens, it means that it travels slower. So you can see here that your hydrochloric acid, your particles of hydrochloric acid, they're moving along, but they're moving slower, they're much heavier. They're taking a longer time to go over a shorter distance than your ammonia. So your ammonia's kind of whizzing along, as it were, and your hydrochloric acid moseying along, and eventually they meet, but more towards your hydrochloric acid. So this is basically a good way of showing that diffusion is affected by the mass of your molecule. So that's the second thing that we can add to our list, as well as temperature. We can, as well as temperature, rather, we can say your mass of your molecule. So we can say mass. I'm not going to bother writing it down, but basically you can see that an increased mass will lead to basically slower molecule, and that leads to a slower rate of diffusion. So there are a couple of other things that would affect diffusion, but nothing that I think is applicable at this level. So that's it for the first video. Thanks very much for, if you're still here, I appreciate it's got quite long, but if there's anything that you think I can do to improve these, obviously this is the first one, do let me know in the comment section, as again, if there is one, and anything else you'd like to see that I can help you with, please let me know, because at the end of the day, this is what this is for. So yeah, this has been The Unnamed. Thanks very much, guys, and I'll see you next time.